All right, folks, in this video, we will be talking about how to make LOL bar charts or energy bar charts. Let me close that parenthesis there. All right, we're going to do this through a way of example. That's the best way, I think, is just to jump right in. So here is the example that we have. There are two snapshots, snapshot A and snapshot B. In snapshot A, we have a cart. That cart is at rest. Its velocity at snapshot A is 0. It is on the ground. Its y value, its height, is 0. And it's been pushed against a compressed spring. So there's a spring and it is compressed. That is the scenario for snapshot A. This compressed spring then pushes the cart. The cart goes around the loop and around like that. And we are going to compare snapshot A to snapshot B. Snapshot B, we are now at a height h above our reference height of y equals 0. And in order to stay in that loop, we know that we need to be moving. We're moving in circular motion here. And so the velocity is non-zero at the top of that loop. And our goal is to analyze this scenario. And the purpose of this video is to highlight the way that we talk about energy and to highlight some key vocabulary concepts. And so we are going to look at this one scenario from 5 different perspectives. So that's our goal, is look at what's going on here from 5 different perspectives. Before we do that, I want to point out that I'm using the word snapshot intentionally. This is like if we took a camera when the cart was here at A, and we went click, there's our photo, and then, I erased some words there, snapshot. All right. And then later on, when it's at B, again, we grab our camera, click, and we're at snapshot B. And that's what we're looking at. So we're not actually going to be looking at all about what happens in between the two snapshots. We are just going to be comparing those 2 points in time. We don't have any time information. We just know what's going on at one point in time and at a separate point in time. All right, so let's analyze this system. Our first analysis is going to be as described there in analysis A. We're going to choose our system to be the cart, the spring, and the earth. The diagram that we see here is called an LOL diagram. It's called an LOL diagram because there's 2 bar charts, which make some L's, and there's a system flow diagram in the middle, which makes an O. So it looks like an LOL. That's why we call it that. And what's going on is the first bar chart on the left is describing where the energy is in snapshot A. That energy could be stored as kinetic energy, which is the energy stored in motion. That energy could be stored in gravitational potential energy. That would be energy stored in a gravitational field due to a height difference between where the cart was and where it is. So that's energy due to the configuration of the objects in our system and where they are. And then there could be spring potential energy. Spring potential energy is energy stored in the stretch or compression of a spring. I'll remind you that it's not enough to just have a spring in order for there to be spring potential energy, but also that spring needs to be stretched or compressed. I'll also remind you that we're using the word spring loosely here to mean any stretchy or compressy thing. So a rubber band would be a spring in this example, a bungee cord, all of those stretchy things. All right, so this is going on the L. The second L is the same, but for snapshot B. Where is the energy stored there? Kinetic, gravitational potential, spring potential. And then here we have another term, which is delta E subscript TH. This term specifically stands for not just thermal energy, but the increase in thermal energy due to the motion that happened. There's always thermal energy unless the objects in your system are at a temperature of absolute 0. But what we're interested in is how much did the thermal energy increase due to the interactions that happened between A and B. Give me just a moment to try and erase the highlights there without doing too much damage to everything else. All right, we're set. And then in the middle is our system flow diagram. We're going to choose to put the objects in our system in that circle. And then we will identify any external interactions by putting external objects outside of the system. So in the LOL diagram, we're actually going to start with the O and then do the L's. So our system, in this analysis, we are choosing it to be the cart, the spring, and the earth. What's in our system is a human choice that we get to make. It doesn't change the physics, it changes how we scientists speak about the physics. It just changes the wording we use. So our system is going to be the cart, the earth, and the spring. All right, so now that we have those written in the system flow diagram in the O, we can now start looking at where is energy stored. And we're going to make bar charts with that. We're going to make each bar made up of separate blocks of energy. So in snapshot A, the cart is at rest. Therefore, there is 0 kinetic energy at snapshot A. In order to communicate to my teacher that I've thought about the value and it's 0, I'm going to put an X at the base of the bar chart. If you leave it blank, that doesn't communicate the value is 0. It communicates to me, your teacher, that I never thought about it. For gravitational potential energy, we are at our reference height of y equals 0. And so again, we are going to choose, so again, there's 0 gravitational potential energy in the system at snapshot A. And then for spring potential energy, there is a spring and it is compressed. And so we can add some energy there. I'm going to arbitrarily choose 4 blocks of energy. That is a choice that you get to make. It doesn't matter a whole lot. All right, so that's snapshot A. Now, energy is a conserved quantity. That means if the amount of energy we have in our system changes, then that change happened due to an external interaction. There are no external interactions, and therefore the total energy must be the same in each snapshot. We are going to represent that by keeping the number of blocks in snapshot A equal to the number of blocks in snapshot B. So in snapshot B, we must also have 4 blocks because I chose 4 blocks in snapshot A. Now, same sort of thought process, one at a time. Kinetic energy. The cart is in motion in snapshot B at the top of the loop, and so there is some kinetic energy. I'm only going to put 1 bar right now. I might come back and add more later. It is at a height above our chosen reference, and so there is some gravitational potential energy. There is a spring, but that spring is no longer compressed, and therefore there is 0 spring potential energy. And this was a smooth track, and so there is no increase in thermal energy. And so I have 4 blocks I need to use, so I should put more in the kinetic and gravitational potential energy values. I don't know if I should do 2 and 2 or 3 and 1 or some fractions. It doesn't really matter for our purposes in this class. I'm going to choose to make this one. Actually, how do I want to do this? I want to make, undo. I want to make the gravitational potential energy 2.5, and I want to make the kinetic energy 1.5. The main reason I chose to do that is to highlight how I would recommend drawing half blocks if you need them. I like the triangles because that's very clearly 1/2 of the square. All right. Now that we've done our bar chart and we've thought about it, we're set to write an equation for energy conservation. And what we're going to say from this equation is that in snapshot A, there is spring potential energy, 4 blocks of it, and that's equal to, in snapshot B, the sum of the kinetic energy and the gravitational potential energy. In other words, this is saying that the 4 blocks we started with is equal to the 1.5 blocks in the kinetic energy in the end, plus the 2.5 blocks in the kinetic and the gravitational potential energy afterwards. So that's our idea for what's going on here. That's not the only way to analyze this system, though. And so let's look at more ways that we could do it. It's the same system, but now in this analysis, we are going to choose the system to just be the cart and the earth, and the environment, what's outside of our system, is the spring. And so our system is cart and earth, and we're always starting with the O, defining our system. And the spring lives outside of that system. So we're going to draw it outside of the circle. Now, what does that mean for snapshot A? There still is 0 gravitational potential energy and kinetic energy in snapshot A, but also there is 0 spring potential energy in the system because the spring exists outside of our system now. In snapshot B, the cart has the same speed and it's at the same height. So we're going to draw the same number of blocks. What happened didn't change. It's just the words we're using to describe the system changed. Still no spring potential energy, and it's still a smooth track. Now, we have some unbalance right now because in snapshot A there is 0 energy, and in snapshot B there's now 4 blocks of energy. Where did that energy come from? Well, it came from the spring. Here's how we're going to represent an external object interacting with our system and adding energy to the system. I think you're going to like this. We're going to draw it as an arrow from the spring into the system, but that arrow is going to be made up of the 4 blocks of energy that the system added in. And so the spring adds energy to the cart Earth system. Those 4 blocks of energy are entering in. That's what that says. We are going to label this with a capital W subscript spring. The capital W means working. This is a working process. The subscript means by the spring on the system. I'll remind you that working, if you forget, I'll put the definition to the right here, that working is a process to change a system's energy through an external interaction. So that's our definition of working. Now, what does this conservation of energy equation look like? We start with 0 energy. The spring then adds some energy in through a working process, and that ends up being equal to the kinetic energy and the gravitational potential energy at snapshot B. Often students ask me, do I need to include the 0 energy for the initial snapshot? The answer is no, you don't, but I wanted to highlight in particular that what we are saying is different than in analysis B, or than in analysis A. In A, we said the energy was always there. In analysis B now, we are saying we started with no energy and we added it through a working process. All right, analysis C. Same scenario. System is the cart. The environment is the spring and the earth now. So not only is the cart's in our system, but not only is the spring outside of the system, but also the earth is outside of the system. What does that mean for our analysis? Well, in snapshot A, just like in B, there's no energy anywhere in our system. The cart can only ever have kinetic energy. It can't have gravitational potential energy alone. That's always energy stored in the interaction between the cart and the earth is now outside of the system. Can't have spring potential energy on its own. There's smooth tracks still. And so the kinetic energy and the amount of kinetic energy didn't change. It's still the 1.5 blocks of kinetic energy in the end because the cart speed is still what it's been in the previous 2 analyses. And so what's going on? Well, the spring is still pushing in 4 blocks of kinetic energy. That's still happening. The earth, however, is removing 2.5 of those. So there's 2 workings that are happening. The spring adding energy into the system, and there's the working by the earth to remove some energy. And so our energy equation looks like this. We start with no energy. We add in 4 blocks of energy via the spring. The earth removes some of that energy, and we end up with kinetic energy in the end. You'll notice that I said plus the work by the earth. We are going to define this later on once we talk about earth or work in more detail. we're going to define that as being a negative value. So this is a negative work. And so we're adding a negative number, which is why it's less than, but we're still going to put a plus sign there. So in other words, what we're saying is the 0 blocks that we started with plus 4 blocks added plus 2.5 blocks removed equals 1.5 blocks. And in this equation that we have, this is snapshot A. This is snapshot B. And this is what happens in between those two snapshots. This is the energy change process. So this is yet another example of initial plus change equals final. It's another way to think about what we are doing here. All right, folks, let's look at analysis D. 2 more of these to go. The system is the cart, the earth, the spring, and the track is now rough. So I want to talk about what that changes. You can probably guess. Cart, earth, track, and spring are all a part of the system. Now in snapshot A, still no kinetic or gravitational potential energy, but now the spring's back in the system, so there are 4 blocks of spring potential energy. In snapshot B, because the track is in the system, there's going to be some energy added to thermal energy. I'm going to make it half a block. That's what's different. The track is in the system, and the surface is rough. So the rubbing from the friction between the cart and the track increased the thermal energy in the track, cart, earth, spring system. So the track and the cart would both be a little bit hotter as a result of this. Their temperature would have increased a bit. In snapshot B, the spring is still uncompressed in that snapshot, so there's no spring potential energy there. The question is, from which of these two, kinetic or gravitational potential, from which of those two did the thermal energy get its half a block? Well, we're still at the same height, and so this can't be any different than what it was in analysis A. This is still 2.5 blocks because we're still at the same height. So the half a block that came from the kinetic energy, or let me start over. The half a block that went into the thermal energy must have come from the kinetic energy. And so our equation looks like this. The spring potential energy in snapshot A equals the kinetic energy at B plus the gravitational potential energy at B plus the increase in thermal energy for the cart and the track. So that's what this equation would look like. All right, last but not least, analysis E. It's the same system, cart, earth, track, or cart, earth, spring. We'll assume a smooth track again. What's different, though, is where we're going to put our reference height. We're going to put the reference height y equals 0 at the top of the loop now. So let's scroll back up to our picture so we can talk about what that means. Here's our picture. What we're going to do now is y equals 0 is going to be here in analysis E. So it's now where the cart is at the end. And then in snapshot A, the cart is below that reference. It's at a negative height relative to 0. Scrolling on down and back, scrolling on back, our system is the cart, the earth, and the spring. The track we can ignore because it's smooth. You don't need to include it if there is no friction. In analysis E, we start with 0 speed. We start with a compressed spring with 4 blocks of energy, but we are also at a negative height. What negative height are we at? Well, it's going to be 2.5 blocks of energy because it's the same height value that we've had in the previous 4 analyses, but it's now negative. And so the total energy in the system is only 1.5 blocks. Some of it positive, some of it negative. And then the spring launches the cart, it goes around the loop. At snapshot B, there's the bell. At snapshot B, the cart, it has the same 1.5 blocks of kinetic energy that it's always had. It's now at the reference height, and so now its gravitational potential energy is 0. The spring potential energy also 0, and we're back to a smooth track. And so our equation in analysis E looks like this. The gravitational potential energy for snapshot A plus the spring potential energy for snapshot A is equal to the kinetic energy in snapshot B, but we're keeping in mind that this is a negative value. This is where our blocks analogy sort of breaks down a little bit, because you can't have negative blocks if we're talking about physical blocks, but you can have negative energy so long as you're consistent. I'll end this with the reminder that's in green in the bottom right-hand corner of the screen, which says for energy, negative is not a direction word. It just is a word that means below 0. So in this class, we've often used negative to mean something like to the left with vector quantities. Energy is a scalar, it's just an amount. So when we have negative, we just mean less than 0. We don't mean to the left. All right, folks, I hope you find that helpful, and that concludes this video.